Okay, so the next set of vocab words or issues that we're going to discuss are frequency, power, and intensity. So the frequency and the intensity are the two main parameters that we're going to be able to set for ultrasound. So it's really important that we understand the difference between the two and what setting one gets us versus the other. So again, back to this definition chart, we're dealing with our frequency, which is the output frequency that determines the depth of penetration. And so our 1 megahertz is going to target 5, maybe 6 centimeters deep, and our 3 megahertz is going to be about 2 to 3 centimeters deep. Now, those depths are much deeper than our superficial heating that we had, as well as the fact that ultrasound doesn't target adipose tissue. It moves through adipose tissue relatively easily. So when we're talking the 5 centimeters and 2 to 3 centimeters deep, we're talking below the adipose tissue as well. So unlike with our cold where we had to know how much adipose tissue we're dealing with, that's not as much of an issue with ultrasound. And then looking at our intensities, the intensity describes the amount of power generated by the unit, so by the ultrasound machine itself. And so we're going to be looking at the power output as an ability to look at how we target the potential effects of ultrasound. And then these various other intensities that we see here, spatial average intensity, spatial peak intensity, spatial average temporal intensity, and spatial average temporal average versus peak, those are going to have to do with the various aspects of the machine. So taking the ERA into account, and then taking also when we talk about a duty cycle into play as well. So let's talk frequency first. So frequency deals with the depth of penetration. So more superficially, we would use a higher frequency, which is 3 megahertz. So things like plantar fasciitis, Achilles tendonitis, epicondylitis, those would be great targets for a 3 megahertz frequency. So again, that 2 to 3 centimeters deep. When we get to 1 megahertz, we're looking at potentially 2 to 3 centimeters deep, even or 2 to 6 centimeters deep, excuse me, really closer to 5 to 6 centimeters deep that our focus is. So where we're trying to target deeper structures. And then I mentioned this briefly in the last video, we have these longer, lower intensity, lower frequency machines, the 45 to 90 kilohertz, that are used more so for bone stimulation and growth and repair. And those can reach up to potentially 10 centimeters deep, that research is showing. But those are not our typical therapeutic modality units. Some machines can have 2 megahertz settings. That's just somewhere in between the 1 and 3. Our 1 megahertz, we'll see in the next slide, is going to be more likely to diverge. Okay, so it's more divergent versus our 3 megahertz that's going to stay more in a column. And again, that has to do with that attenuation and that need to get down deeper. We're going to lose some of that. The higher frequency, so the 3 megahertz, the energy is going to be absorbed more rapidly. Okay, so it's going to end up being more superficial because of that energy absorption. The lower frequency, again, our 1 megahertz, it's going to penetrate deeper. It's also going to have longer lasting depth, okay, for our heat. So it retains heat twice as long, but it's going to heat slower than our 3 megahertz. So we get about 0.2 degrees Celsius per minute with our 1 megahertz with a certain setting, certain output setting, our intensity setting. And we get about a 0.6 degrees Celsius per minute increase. So we increase more rapidly with the 3 megahertz because it's more superficial and absorbing faster, but we retain the heat half as well as we do with the 1 megahertz. The 1 megahertz also decreases the risk of what we call unstable cavitation, which we'll talk about when we start talking about the effects of ultrasound. So this just kind of is a visualization of what we just talked about. The 3 megahertz is going to be more superficial, about 2 to 3 centimeters deep, but stay in more of a column. More is going to be absorbed. We're going to have higher increase in intensity per minute of heat, as well as we're not going to retain that heat as quick as well. And then 1 megahertz, we go deeper, 3 to 5, maybe up to 6 centimeters deep, but we get a more divergent beam, as well as then we heat a little bit slower, but we retain our heat. So the superficial on this is about a third as long to absorb to the proper heating temperature than the 1 megahertz. So it's going to take about 3 times faster at heating than the 1 megahertz. Now talking about power intensity. So power, which we measure in watts, okay, is a measurement of the energy output. Okay, what we're going to talk much more about is intensity, which is watts per centimeter squared, which is taking that amount of the energy that we can produce, okay, and putting it over the area that we're treating. So when we set intensity, so when we set frequency, we were setting our depth, our target depth. When we set intensity, we set the effects that we want. So whether we want thermal or whether we want non-thermal effects. Now, every time we use ultrasound, we get both of those things, thermal and non-thermal effects. If we have our settings low enough, however, we can apply the energy at a level that has very little thermal effects, and that the body can then diffuse that energy and that thermal increases out of the tissue, so that we essentially get no increase in temperature. But then that maximizes the non-thermal effects that we get. If we have a higher intensity, then we're going to have much more energy in that area. We're going to actually raise temperature, and so the main effects we're going to be seeing are thermal. The non-thermal effects are still there. They're just a little bit more overshadowed by the goal of raising the tissue temperature with the thermals. So higher intensities tend to be for our more thermal situations, lower intensities are more non-thermal. And we can also manipulate that with how much time that the beam is on, and we'll talk about that when we get to duty cycle conversation. So the intensity really does tell us about the strength of the waves at any given location. So because we're dealing with an area, we're talking about the location within the tissue. Now what we normally talk about is what's known as the spatial average intensity, which is the power output divided by the ERA. So this is the amount of power that the machine is producing divided by the effective radiating area. Okay, so what this is telling us is that the area, the ERA, plays a significant effect in how we get to our intensity. So for example, if we use 10 watts of power, okay, but we had an ERA of 5 centimeters on one machine and we had an ERA of 10 centimeters on another. The machine that has the larger area, the 10 centimeters squared, okay, is going to actually have a lower intensity because it's going to be 10 watts over 10 centimeters squared versus the ERA that was smaller, that was 5 centimeters squared with that 10 watts, because we're going to be delivering the same amount of power but over a smaller area. Okay, that's important to keep in mind. So the ERA plays a role in that. Two other terms that show up, spatial average peak intensity and spatial average temporal intensity. So the spatial average peak, okay, is when we talk about the on time of the pulse. So when we end up setting duty cycles, the on time of the pulse tells us our peak. So what is our power over our ERA when the machine is on? Okay, so it ends up being close to our spatial average intensity there. The SATA, so the spatial average temporal intensity, gives us the power of the ultrasound delivered to the tissue over the given time. So it takes into account a time, and we only talk about this when we use pulse ultrasound. So if we have the ultrasound on for our duty cycle only about 50% of the time, okay, then that automatically decreases our spatial average peak intensity by half. So if we had 50% duty cycle of a 2 watts per centimeter squared spatial average intensity, we really, over that entire treatment, are really only getting about 1 watt per centimeter squared because it's only on 50% of the time. And so this chart just kind of shows you, again, how the ERA affects the overall intensity and the power being produced.